Hello everyone, my name is Atharv and I'll be starting with the presentation of the paper titled Chrono, Meticulous Hotness Measurement and Flexible Page Migration for Memory Tiering. As a background, there has been a significant rise in demand for large and fast memory in data centers, which are used for various workloads involving high performance computing, model training for ML, and in-memory database services. So tiered memory architecture basically refers to segregating memory based on their capacity and speed. So broadly, we can categorize them into two types. One is fast memory, which consists of DRAM, and it has a slightly low latency of 50 to 90 nanoseconds, but at the cost of a limited capacity. Then we have slow memory, which consists of NVM over CXL, which has a higher latency of 150 to 270 nanoseconds and a much larger capacity. So NVM stands for non-volatile memory, and fast non-volatile memory is basically SSDs or flash memory over CXL, and CXL stands for Compute Express Link. It is basically an interconnect protocol for high speed and high capacity CPU to memory connections on PCIe, which is basically a bus. So the tiering goal for the paper is to keep the hot pages in the DRAM and move cold pages to the slow tier. So hot and cold, basically temperature refers to how frequently or how important certain pages are for a process. Moving on. The main problem which the paper aims to solve is the precise identification of hot pages, which are those pages to be promoted, and cold pages, which are to be demoted, with a relatively low operating system overhead. The core problem is that the existing solutions all have drawbacks. They use coarse, inflexible hotness measurement and have rigid migration rules, which proves to be inadequate. The solutions are either temporally imprecise or spatially imprecise. Coarse-grained access patterns refer to aggregating information about page accesses too infrequently, that is over large time windows, which misses activity that occurs per second or in the per millisecond range. Moreover, binary information about access or no access misses the intensity with which a page was accessed. So it gives an improper judgment of hotness. Coming to spatial imprecision, many solutions determine activity of large memory regions rather than recording per page access patterns, which leads to low spatial resolution. Both of these combine to give wrong or unnecessary demotion information, and waste the migration bandwidth and pollute the DRAM. Data centers consist of multiple CPUs operating with their own DRAM. Such a system is termed as NUMA, which stands for Non-Uniform Memory Access System. In this, the physical memory space is divided among multiple CPUs into NUMA nodes, which are basically memory nodes. So a CPU can access memory belonging to a different CPU, but such an access will be slower. In the page migration scheme used by NUMA, the kernel scans only a portion of a process's address space and marks those pages with the prot_none flag. Any accesses to those pages will result in a page fault. The kernel will check the CPU which caused it, and a migration to the CPU's local memory will occur if the NUMA node of the page does not match with that CPU. So if a certain CPU accesses a page which happened to have been scanned, and that page belonged to a memory node mapped to a different CPU, then it will bring that CPU to its own local memory. Hence, it can access that page with a relatively low latency. So extending this scheme to tiered memory architecture is not very fruitful. In tiered memory, the slow tier, which consists of the non-volatile memory, is represented as a NUMA node that has no CPU. Hence, any access to a scanned page that happened to be in the slow node triggers a migration to the CPU's local node. As you can see, this is similar to the MRU policy, which is the most recently used policy, and it using a single flag, where access frequency is not taken into account, which can lead to misidentification of hot pages in the slow tier. Moreover, a narrow sample of scanned pages will fail to capture all the truly hot pages, whereas scanning a large sample is too slow. So many papers have been published aiming to accurately identify hot and cold pages. The solutions can be broadly classified into three categories. The first category relies on software page faults and scanning windows. In the auto-tiering solution, software page faults within the recent 8-page scanning period is represented as an 8-bit LAP, least access page vector. It is used to distinguish hot and cold pages. In TPP, transparent page placement, the existing NUMA migration scheme of using page faults is combined with maintaining active and inactive LRU lists to estimate a page's age, and using that, it develops criterion to determine if whether a page should be migrated or not. Both of these solutions lack fine-grained page access frequency measurement resolution. In both, the kernel scans pages only once every minute. So it misses the activity that happened per second or per millisecond within that 1 minute. While shortening the scanning period could theoretically refine frequency measurements, it also leads to substantial page fault handling overhead. The second category relies on using hardware flag bits. Based on how the pages are accessed, the bits are set and LRU lists are maintained to determine whether a page migration should occur or not. One example is multi-clock, which optimizes the page reclamation algorithm named clock by constructing multi-level LRU lists and selecting migration candidates from the top and bottom lists based on reference PTE bits. The clock algorithm is also called the second chance algorithm, and it is an approximation of least recently used algorithm to decide pages to swap out. Again, hardware bits don't capture frequency or intensity of access, hence it is coarse-grained. The third category uses PEBS counters. So PEBS stands for Processor Event-Based Sampling. They are built-in counters that are used to track various statistics about memory accesses. It is a feature supported by modern processors. For example, it can maintain a counter for L1 cache hits, L1 cache misses, or number of load operations on a specific memory region, etc. Whenever performance counter exceeds a certain threshold, a record will be written to a pre-allocated buffer, which contains the virtual address of the page that caused it. For example, HeMem utilizes PEBS counters to represent the memory access frequency and classify hot and cold pages based on fixed thresholds. Memtest, on the other hand, proposes a global histogram binned by hotness values and uses dynamic thresholds to decide page migration. Again, the PEBS-based tiering solutions are mainly optimized for huge pages of the order of megabytes and face considerable obstacles when applied to base page systems.
So, hello friends, I am Purab Agarwal and today I'll be discussing about the design of Chrono OS. So, Chrono OS is a novel OS level tiered memory management system and it deploys a timer based uh, hotness measurement scheme. Hotness is just how frequently a page is getting accessed. It's built on a mainline Linux kernel and it employs non-uniform memory access and to architecturally separate slow and fast tiers. So in our tier memory management, we have obviously two main important things, which is page promotion, which is putting hot pages from cold slow memory to fast memory, and page demotion, which is putting cold pages to from fast memory to slow memory. And we have this separate thing, second thing called parameter tuning, which is essentially based on the user process, put a dynamic variables of threshold and parameters so that this promotion and demotion works according to the process and user's need. Now, how does this page promotion happens? It happens using this timer-based hotness measurement, which is essentially captured idle time, a variable, which is by definition the time gap between the page scan and page fault. It is a reliable metric that negatively correlates with the access frequency. So let's see about first the first thing. How is this CIT measured? So it is measured through a ticking scan. First, we scan a range of virtual addresses and we unmap them, making them unaccessible for the CPU, and we record that scan timestamp in a variable at the time when you unmapped it. Then when a page fault happens, by accessing that page, the system handles this trap by going to the page fault handler, and this page fault handler records this PGF timestamp. So the CIT is calculated as PGF timestamp minus scan timestamp. So obviously a page which is being accessed more is having a less CIT value and it is hot, and a page getting accessed less has a greater value and is scrolled. So now we have a dynamic variable called CIT threshold, which we'll later by different methods fix it. Now why CIT is a good metric? The only thing it cost is an extra 4 byte memory timestamp unit, which is very negligible as compared to a page. So it has low overhead. It has high frequency since it's a 4 byte timestamp. So it is a high resolution value which can measure time in milliseconds. So if you're measuring time in milliseconds, you have a least count of milliseconds. So the upper bound of your frequency is 1000 accesses per second, which is a quite good metric. And it is a decoupling. So decoupling means that it doesn't matter how frequent your scans are happening. If your scans happening 1 minute or 2 minutes, your CIT value will remain same, which is, for example, 10 milliseconds. So its decoupling is a good thing, which traditional methods are although coupled, that it matters on how frequent you are doing the scan and your counter value changes upon those coupled weights. So this is decoupled. And the authors have also shown that if you assume a Gaussian distribution of memory getting accessed, so your CIT value is inversely proportional to that. So it is negatively correlated. So it's a good estimator in fact. Now, conditional page promotion. Now, measuring CIT once can impose many problems, like it can be by fluke, one cold page can get accessed and you might have just measured due to randomness a very small CIT value. So That's randomness is a problem, and this fixing a threshold value is a problem. So threshold problem we resolve by putting it in as a dynamic value and dynamic variable, and this randomness is resolved at how do you resolve randomness? If you are not sure that a value is good or not, what do? You do that method, you repeat that method again. So this candidate filtering happens. As you can see in this previous slide, we had measured the CIT value and we considered some as hot, and then we measured it again. And again, if the second time also it passed the test, then we had put this into the promotion queue. So it has to pass the test 2 times to get decided as a promotion queue. So this candidate filtering helps us do that. Yeah, so this is the same thing that you scan it once, and the one that has those that have passed the test, you put it in a candidate page set, and then you scan it the second time, and those that have passed the second time also, which were already in the candidate page set, you put them in the promotion queue. So why this doing this 2 times is the perfect balance? First, stability, that it removes randomness of one CIT value getting low CIT value by fluke, and it tells us the maximum between those two, which is in fact a good metric as explained in the appendix B.1 of the paper. And this is also efficient, that one would argue that three, why not do 3 or 4 or 5 or 6? So doing 2 is in fact very stable, because doing more rounds increases more page faults and more overhead cost of traps and all. So by simulations also 2 turns out to be the optimum one. Now we have parameters like CIT threshold that we have to optimize, and the promotion rate limit that we have enqueued in the value, but now we have to also decide in what way we have to promote pages from that queue. So we have 2 methods. First is the semi-automatic and second is fully automatic. So in semi-automatic, the rate, we assume that the user knows his process. So he has already given us the promotion rate limit, and the threshold is essentially calculated by this formula, which just tells that delta TH is 1 minus R gamma TH. So R is rate limit by NQ rate. So if R is less than 1, we intend to in fact uh, increase the threshold value, because it's having low promotions. So this is positive, and if R is, and vice versa. And fully automatic, let's see. So fully automatic is done by dynamic CIT statistic collection, another component. What it does is randomly takes a few pages from hot tier and slow tier, and it plots their distribution using the histograms. So it looks something like this. Assuming this is hot, come like this, and this is cold. So this overlap part tells us about what should be our threshold, and it in fact tells us the misplacement ratio also between the hot and cold pages in the slow and fast tier. So we try our hot pages to be in the fast tier and cold pages in the slow tier. So using this, we get the threshold value, and also we get the misplacement ratio, which tells us the optimum promotion rate limit. Now demotion, we put a pro watermark, which is essentially a watermark above the standard high watermark in Linux, and the gap size is decided by this formula. So if the free space available in the fast tier is less than this pro, we start to remove pages using the LRU policy. Page thrashing is essentially that you have just demoted a page and then again promoting it. So system is wasting its time in promotion and demotion and not really doing something. So what you do is as you demote a page, you store a demoted flag, and if that also note that taking scan. So if that demoted flag is there on a page and you again promote it, you note that as a thrashing event and calculate thrashing rate. So if thrashing rate gets too high, means 20% of all promotions are thrashing, then you have to reduce. The system is aggressive, so you have to reduce the aggression. How do you do that? You half the promotion limit rate. So the system promotes less pages and be less aggressive. Now we have discussed all our features of Chrono OS. Chrono OS also supports huge page support. The taking scan remains the same because it's the same thing. It doesn't matter the page size. The threshold adjustment, since the 2 MB has 512 times more data than the 4 KB, so it has to be more valuable to come in the fast tier memory. So the threshold is just divided by 512 times. Now changing DCSC statistics is that you had initially putting in, we are putting a 4 KB page into to the power ith bucket. Now instead of putting a 2 MB page into to the power ith bucket, you are assuming that this 2 MB is comprised of 512 4 KB pages, and you are putting them in. You are assuming each of them has 2 to the I into 512, which is 2 to the power I plus 9, I plus 9 bucket. You are putting 512 value, which is essentially the same thing. So now you have this DSC statistics in corresponding to the 4 KB pages, and you can do it as the same thing. So yeah, I think that's how you design this Chrono OS. And let's see its evaluation and the analysis in the subsequent slides. Thank you. Bye bye.
So good evening friends. Today we are going to look at the implementation of the Chrono paper after having discussed the algorithm and design in detail. So Chrono is implemented in Linux kernel version 5.18 with 1.9k lines of changes. So now all this code is publicly and easily accessible through GitHub. So now Chrono is implemented by using a sysctl option NUMA tiering. Now you might be wondering what a sysctl is. Sysctl is an option to enable, disable or tune kernel behaviors without recompiling or rebooting the system. When it is 1, we use the Chrono CIT metadata system, whereas when it is 0, we use the default NUMA based system of Linux. So now you might be wondering what exactly code is added. So we have maintained per page 4 bytes which store the CIT metadata for that singular page. And we also have an X array, which is an kernel-like array index structures, and they store that from possible pages which are the candidates for the promotion from slow tier to hot tier. So now the storage here is approximately 32 kilobytes, which is not really much when it comes to efficiency. Next, we go to there is a 2 scan process after putting the candidates in X-array. So in the first scan, we assign the values of CIT to them. Now, how we assign them? We just on the first scan, we make we sample some pages and mark them as inaccessible by raising their prot non flag. So when these flags are inaccessible, next time when we access these flags, a page fault will be raised, and the value of CIT will be the timestamp of the current when the fault is occurred minus timestamp of the previous scan when it had occurred. So CIT values are then assigned, and in second scan through this X array, we just make sure that values of CIT which are above the threshold are promoted into the next tier, which means hot tier, like from cold tier to hot tier. Next, you might be wondering what exactly is the threshold limit. Well, that is a parameter, and it is tuned here by 2 methods. First one is auto tuning, and next is DCSC. In auto tuning, it is quite simple. We just maintain a migration limit, and the promotion NQ rate is defined. So basically, we limit the number of promotions from cold tier to hot tier by a fixed number, and after that, the threshold limit gets adjusted according to that limit. Next, we go to DCSC. Now, DCSC is quite a good tuning algorithm. Here, we maintain a PG prot flag to mark the pages sampled. So, first of all, P%, P is a parameter, P% of pages are sampled and put into 28 buckets based on their CIT values. And now each bucket contains hot and cold pages. So, what we try to do is like hot pages are maintained in the above tiers and cold pages are maintained in lower tiers. There should be a contradiction between this arrangement. Next, we go to thrashing monitor. Thrashing monitor, we define thrashing as when a page gets demoted and then gets promoted in the next run itself. So it's called a thrash, and on a particular thrash, we halve the threshold limit. So according to that, threshold limit gets to its optimal value. Next, CIT always stores its CIT metadata per page, even if the page size is in megabytes or gigabytes. It doesn't contain a shared variable for entire page. It will contain CIT metadata for each individual pages of that huge page. Next, we go on to evaluation platform. We test it on Intel Axion Gold CPU, and we have used 2 benchmarks, PM Bench for micro benchmark and Graph 500 for macro benchmark. And we have compared it with Linux baseline 5.18 and memtest. And there are a couple of real-world applications as well. Next, we go to PM Bench micro benchmark throughput performance. Now, what here we observe is that there's a 216% rise in the throughput compared to the Linux of default NB system. Now you might be wondering how does that occur? That occurs because millisecond range CIT measurement to identify true hot pages is working at page granularity at absolute page levels. Also, the latency decreases by about 79% as Chrono is able to identify hot and cold pages efficiently and put the hot pages in the DRAM memory, which is the fast access memory, and cold pages in non-volatile memory, which is the slow memory. Next, we move on to how fast memory access ratio. Then it has also improved 49% to 77%, indicating good placement of hot pages in DRAM. Next, kernel overhead gets reduced by 2.1%, but since we are getting so much benefits in performance, increasing a kernel overhead bits seems a bit relevant, like not a much of disadvantage here. Next, we move on to what is the effectiveness of hot and cold page identification here. So for that we tested, we put pages, sampled the pages and put them into 50 groups according to their size. So what happened in the other systems was hot pages were concentrated in the upper tiers, upper groups only. Like if we are in 0 to 50, in 0 to 10, most of the hot pages are concentrated. Then concentration of hot pages decreases as we go down. Now that is very bad. So Chrono ensures uniform distribution in all groups of hot and cold pages. So we tested it and found it to be really good, better than Memtis and Linux. This happened because graph-based algorithms right now, they keep a lot of warm pages and are not able to handle them correctly. In Chrono, there is a precise placement of hot and cold pages. Next, we go on to macro benchmark Graph 500 and compare the performance and results. So we once again observe there is a 2.49x speed up over the default Linux NB system. So once again, what might be the causes for it? So one here is Chrono's absolute precise CRT gives fine frequency resolution, plus there is a balanced migration since we have put a migration rate. So not all cold pages go into hot pages immediately. So this migration limit ensures that only the good ones candidates go from slow tier to hot tier. Next, we also do a sensitivity analysis and see that all parameters there go to an optimal value and then decrease. Now, a couple of these parameters like P victim is a good one. It is the ratio of pages that are sampled in DCSC, which if we keep it too small, then sample will not contain information of the entire data. But if we keep it too large, then kernel overhead will increase because we are taking too many samples. Next, scan step and scan period are basically page fault rate, like they indicate them. So if we keep them too large, kernel overhead gets reduced and ultimately throughput decreases. So we have to keep a balance so that there is not much overhead and throughput also is at an optimal level. Plus delta step is adaptation step for CIT, threshold adjustment, and if we keep it too small, then there is a slower convergence and suboptimal performance. Here also we have to keep a balance. Next we move on to two real life applications, Memcached and Redis, and then we will move on to further paper how it can be done. So thank you guys.
Hello, so I'll be continuing from here. To see how Chrono performs in the real world, we tested it with two demanding applications, Memcached and Redis. Memcached is an in-memory caching system designed to speed up web applications by storing frequently accessed data, like database results, in RAM to reduce load time. While Redis is a fast in-memory data store, often used as a database or a cache. The goal was to create a high-pressure environment, so we set up a 160 GB key value store where the active data was intentionally larger than the fast data DRAM. This forced the system to make very smart decisions about what to keep in the fast memory. Looking at the graph, the key finding is clear. The green bar, Chrono, consistently delivers the highest throughput. It significantly outperforms all other state-of-the-art systems. The obvious question arises, why does Chrono win? First, systems like auto-tiring and TPP are too coarse-grained. They can't distinguish truly hot pages from merely warm ones, leading to poor performance. Secondly, Memtis, which relies on huge pages, suffers from memory bloat. It happens when only a small part of a large page is actually accessed. In this test, it had a 145% bloat rate, wasting fast tire space by promoting large 2 MB pages when only a tiny fraction was actually hot. This is where Chrono shines. Chrono's success comes from its fine-grained measurement at the base page level. Even under intense pressure, it precisely identifies and moves only the truly hot 4 KB pages, avoiding the bloat and fragmentation issues that hold back other systems, leading to a much superior performance. Moving ahead. Now, a critical part of the research was to justify the design. This slide shows an ablation study where we built Chrono up piece by piece to measure each component's contribution. The graph shows performance in terms of throughput across different read-to-write ratios, going from read-heavy to write-heavy as we move from left to right. The light blue bar here represents the performance of the Linux system taken as a baseline. First, we have Chrono Basic, the orange bar. This version only implements the core one-round CIT measurement. As you can see, this alone provides a massive performance improvement across all RW ratios, which is powerful evidence that the fundamental idea of using timers instead of counters is the right approach. Next, Chrono Twice in purple adds the 2-round stability filter. We see another significant performance jump. This confirms that filtering out noisy measurements to prevent bad promotions is crucial for efficiency. We also tested a 3-round version called Chrono thrice and found its performance was similar, proving that 2 rounds are sufficient without adding unnecessary overhead. Finally, the green bar is Chrono full with the fully automatic DCSC tuning enabled. This version is consistently the best performer. The DCSC scheme, as the paper states, adaptively adjusts the key parameters to reduce redundant page migrations. It does this by creating statistical heat maps of memory usage, allowing it to fine-tune the hotness threshold and migration rate in real time. The key takeaway is that Chrono's strength comes from how these parts work together. The precise measurement, the stable filtering, and the smart adaptive control all combine to deliver the final superior performance. Moving ahead. Okay, so Chrono performs well, but what's the cost? It's actually very efficient. First, the kernel time overhead is modest. Chrono adds only a 2.1% cost over the baseline, where 1.8% of it is from the DCSC to self-tuning scheme alone, showing that the core CIT timing mechanism is highly efficient. Next, its memory footprint is negligible. The CIT needs just 4 bytes per page, or about 0.2% of physical memory overhead, making it lightweight and scalable. Finally, the automatic tuning is highly effective. The system analyzed the workload and converged the CIT threshold to 200 milliseconds, which precisely identified the hottest 25% of pages, perfectly matching the available fast memory and proving that it's truly data-driven and adaptive. Moving ahead. Okay, so Chrono's effectiveness comes down to 4 core strengths. First, first is its novel timer-based measurement, CIT. This is a paradigm shift from counting accesses to timing idleness, which removes the measurement precision from system overhead. We get extremely precise data from the timers down to the millisecond without needing to constantly scan the system, which drops performance. Second is its fine-grained base page accuracy. By tracking hotness on 4 KB pages, it avoids memory bloat and fragmentation issues that plagues huge page systems. This is a huge benefit because other high-precision systems like MemTIS are forced to use 2 MB huge pages because their sampling method is statistically unstable on 4 KB pages. Next, the fully automatic self-tuning DCSC scheme is the system's brain. Chrono builds heat maps showing hotness in fast and slow memory, compares them to find misplaced pages, and auto-adjusts migration policies in real time. This eliminates the need for manual tuning. And finally, it has a robust and lightweight design. Features like 2-round filtering ensure stability, all while operating with negligible memory and kernel time costs. Moving ahead. Limitations. Of course, no research is complete without discussing its boundaries. First, Chrono is a kernel-level system. This makes it transparent to applications, but the trade-off is that it can't access application-specific statistics like a user-level system could. Second, Chrono has a strict focus on migration policy, that is, deciding what to move and when. But it doesn't try to change the underlying mechanism of how pages are physically copied. It doesn't optimize low-level process of actually copying the page from slow memory to fast memory. Thirdly, its CIT measurement principle hasn't yet been tested on emerging architectures like non-inclusive memory tiers or new caching paradigms. How it would adapt to these complex future systems remains an open research question. Moving ahead. Okay, so building on those limitations, the paper points to several exciting directions for future work. The first is to integrate advanced migration techniques. The idea is that you could take Chrono's policy for identifying hot pages and pair it with other advanced mechanisms designed specifically to accelerate the physical page copy process. Second, we can explore hybrid kernel or user-level management. Chrono's kernel-level design ensures full transparency, but this limits visibility into app-specific details. A future hybrid model could keep this transparency while using statistics provided by the user, making migration more context-aware and efficient. Finally, a key area for future research is adapting to future memory architectures. This involves extending Chrono's timer-based mechanism to work with more complex future systems like non-exclusive memory tiers, or new caching paradigms. Okay, moving ahead. So, to conclude, Chrono is a novel OS-level system that effectively solves the long-standing granularity mismatch problem in memory management. It introduces the timer-based CIT, enabling fine-grained, low-overhead hotness measurement, the foundation for its adaptive self-tuning and proactive management. As a result, Chrono achieves major performance gains and consistently outperforms state-of-the-art systems with more precise and efficient page migration. This slide also lists the main systems and benchmarks used for evaluation, and notably, the work is fully open source. The source code and the evaluation artifact are available on GitHub and Zenodo respectively. With this, we conclude our presentation on the research paper. Thank you.